A calorimeter is a device used to measure heats of reactions. The apparatus is designed with thermally insulated walls. If a temperature change of delta T is observed, then the heat flow that would be needed to reverse the temperature change is your calorimeter constant time your delta T, change the sign, where you see calorimeter is the heat capacity in all its contents after the reaction has occurred. Therefore, the Q of the reaction is equal to a negative of your calorimeter constant time your delta T. Now, what's happening here is that you're measuring the surroundings of the system, and that's the temperature you're getting. So we have to put that negative sign to change the sign, because this is of the surroundings, and we want the reaction, which is the system. So based on the data we're collecting data on the surroundings, I got to change my sign for that of my system's results to reflect it. It's going to be the same quantity number, but it's going to be a different sign in the sense of exothermic or endothermic process. Another way to look at this is the Q of the reaction is equal to the negative heat of the calorimeter, or in other words, opposite in direction of into or out of the system. Important concept to remember is that we typically are looking for the heat of the reaction, that system, but often we measure the data involving the surroundings of that calorimeter. This means we need to change the sign of the heat value calculated to determine the heat of the actual reaction or system, which is what we're looking for. So Q reaction, that of the system, is equal to the opposite of what you calculate with your calorimeter constant time your delta T. The Q of the reaction, your system, is the opposite of what you get if you measure in the surroundings, if we're talking about heat capacity, specific heat, time mass times delta T. If you measure in the system, like we did in the first couple of examples we did in this section, then you measure in that of the system, therefore you don't change the sign. It is telling me the heat of the system. So it kind of depends whether am I measuring the system or I'm measuring the surroundings. If I'm measuring the surroundings, I got to change the sign. If I'm measuring the system, I do not. Let's look at an example. When 23.6 grams of calcium chloride was dissolved in water in a calorimeter, the temperature rose from 25 degrees C to 38.7 degrees C. If the heat capacity of solution in the calorimeter is 1,258 joules per degree C, what is the enthalpy change per mole of calcium chloride? Well, the interesting thing here is that what you're measuring here is that of your surroundings. That's of your water. Okay, you're not measuring the actual calcium chloride. So we got to account for this in our equation, which means we got to change the sign. We've given our correct calorimeter constant, which is 1,258 joules per degree C. So if I multiply by my change in temperature, that would tell me the amount of heat associated with this process. But you got to realize the amount of heat that we're getting is for 23.6 grams. So I'm going to have to account for that to give me a ratio of the amount of heat per gram, or in this case, per mole, is what we're looking for. First, this problem involves plugging the proper values into the equation to determine the ratio of heat generated for the reaction. So Q reaction is equal to a negative C calorimeter times delta T, which is negative 1258 joules, meaning per degree C, time my temperature change. So this is my T final minus my T initial. My degrees C's cancel, leaving me in joules, which tells me I get 1.72 times 10 to the 4th joules. This tells me this is an exothermic reaction and that it's releasing heat. Okay, that the system is releasing heat. And that's where this sign is coming in. I'm changing the surroundings information to the system, so therefore I know what the system is doing. Now this is the amount of heat released per 23.6 grams of calcium chloride. You got to realize this amount of substance is what produced that heat. Okay. Now sometimes you might want to just divide by the amount of mass just to give you a joules per gram basis. So then you can have this as a calibration term that I know how much heat's given up for every gram of calcium chloride that I dissolve. Okay. This particular problem, we're not looking for that. We're looking per mole, so I'm going to have to take that grams and convert it into moles. So this is the amount of heat released when 23.6 grams of calcium chloride are dissolved, not per 1 mole of calcium chloride as requested in the problem, so we're going to have to account for that. This problem is looking for a ratio that will give us a conversion factor that can be used to calculate the amount of heat associated with different quantities of calcium chloride in future experiments. Once I have this ratio, all I need to know is how much substance got, and I can figure out how much heat is going to be generated. Basically, we will convert grams to moles, giving us the conversion factor between heat and moles as requested in the problem. As I said, you could have just as well left it as heat per grams, but this problem acts per mole. So I have my 1.72 times 10 to the 4th joules per 23.6 grams of calcium chloride. So then I got to convert grams to moles to my molar mass. So 111.1 grams per calcium chloride. My grams cancel. So now I have joules per mole, which is what I'm looking for. So if I multiply out the number, I get 8.10 times 10 to the 4th joules per mole of calcium chloride. So if I have 1 mole of calcium chloride, I know that 8.1 times 10 to the 4th joules of heat will be released. Okay, joules of heat will be released. That's what that negative sign is telling me. This factor can be used to calculate heat release for any amount of calcium chloride. Homework 54.